Hey there, class. We're here today. We're going to look at an example of rigid body equilibrium. This is our second example, and this is related to example 1, which I will put a link to that video, so you can check that one out as well. But this one is the same uniform beam, same mass. It's supported in the same exact locations as our previous example. Now the difference here is we're going to be placing a 0.9 kilogram mass on the right hand end. So that's going to place an object of some sort down here, okay, where this thing here, we'll call it, let's call it mass 2. And mass 2 is 0.9 kilograms. So this, of course, is going to kind of push down on this end and cause it to try to, rotate in the clockwise direction around this point. So what we're going to do is we'll start off with our free body diagram. We'll take a look at the original free body diagram that we had drawn and see how this changes it. So originally we had drawn this where we had a normal force up here due to the support 1. We had an upwards force due to support 2. And of course we had the center of gravity being attracted down towards the earth here. In this problem, what we're going to end up having is we're going to end up actually having another force that's applied down this direction. All right, let me try drawing that a little straighter than that. Basically, this is going to be a force, and it's going to be a larger force than the force of gravity. Let's call this a force applied, and this is on the beam, and it's because of mass, and what did I call it? Mass 2, I think. Let me scroll up here once real quick. Yep, I called that mass 2. So basically that is a new known, so mass 2 equals, 0.9 kilograms, I guess, right? Okay. All right, so our strategy is going to be very similar to what it was before. Basically, I'm going to look at the torques, because again, this is a rotational equilibrium. We effectively have our torques. Now, originally we had, let me zoom out a little bit, we had placed the point of rotation over here on this point here. We can do that again. In fact, since I have all my directions or my distances measured from there, I think I'm going to set my point of rotation at the same exact place for this one. So we'll put the point of rotation here. Again, you can pick any point of rotation you like. We're going to consider this is our point of rotation, and everything that causes it to rotate or has a torque in the clockwise direction, we're going to consider to be positive. And again, this is consistent with what we did before. So that's not going to change any of these numbers here. They're all going to be the same. The difference here is the distance to where the applied force is going to be, let's see, our beam was 1 meter, so that would be, let's go back up here to my picture. Yeah, it was 15 centimeters in, so that means from here to over here will be the 1 meter minus the 15, so that's going to give me what, 0.85. Okay, it'll give me 0.85 meters for that distance. Okay, so looking at our situation here, basically this equation still applies. We have our gravity torque, that's going to go clockwise. The torque due to this support right here is going to cancel out because it's right at the point of rotation. We have our torque due to 2. It's going to be an upwards torque. That seems to make sense. And the only thing we really need to do now is we need to include another torque. So I'm going to go ahead and include the torque, and this would be in a positive direction because that one's going to tend to make it have a torque in the clockwise direction. So I'm going to call that torque A due to object or force A, and that has to now equal 0. So that's going to now change pretty much from this line down. It's going to change everything. I'm going to pause the video, make those changes, and we'll pick up here in just a moment. So I've made those changes. I've now solved for the Fn, and again, some algebra happens here. I've skipped over probably a couple steps, but I assume that this point, we can do the algebra to isolate the normal force here too. And again, these are all values that I know. I will eventually go over here and implement. But for now, let's actually move on to the second part of this, which again was to find this normal force 1 right here. Now, once again, the reason that we chose this point of rotation was because this actually canceled this normal force out of our equation because it doesn't create any torque about this point of rotation. We could reset our point of rotation at any other location on this beam. Actually, it doesn't even have to be on the beam. It can be at any point. But it's often convenient to put it on the physical beam itself. Not always, but it would be. However, because we now or would know the gravity force, the applied force, and after solving our strategy 1, we will know this normal force here. We have 1, 2, 3 forces, and there's only a fourth one unknown. This is where we can apply Newton's second law of equilibrium, which means that all the forces basically have to cancel out. And that's a much easier thing to do because we don't have to worry about distances from the point of rotation. It's pretty much just adding and subtracting. So that's what I'm going to do. I'm going to set that up down here. And again, this was originally what we had. We had the normal force 1 up. We had the normal force 2 up. We had the gravity force down. And really the only change now is we're going to subtract out that applied force. And that's going to equal 0 because again, this is not accelerating up or down. It's in what we call translational equilibrium. Now, some of you that are a little more savvy and understand something, you're going to notice that there's actually a red flag somewhere here. I'm not going to tell you what it is yet. We will see in just a moment what that red flag will be once I do the implementation. So let's continue with this. Basically, when I solve for the normal force, what that's going to do here on the right-hand side is we would have to add in the applied force as well. Bringing that over would actually make it a positive. So I'm going to go ahead, pause the video, I'm going to implement, and we're going to see what we get. Okay, here we are, but we're back, and I've just implemented my strategy. When I solve for the normal force 2, that's the support here on the right-hand side, and actually end up with about 15.3 newtons. Now, let's compare that to when we solved this before. Before, it was actually only 2.8 newtons. Let me zoom out so we can see this whole thing on here. But only 2.8 newtons. Now, let's think about that, why that even makes any sense. That's a huge increase, right? From 2.8, that's just around 3 newtons, to about 15 newtons. That's roughly 5 times more force that it has to support. And that's all because of this extra mass that's placed over here. Where before, this thing here was only really partially responsible for supporting this, this 0.4895 gram bar. It is now having to support almost a kilogram extra. That makes a huge difference. The rotational effects happen here as well. All right, so I mentioned that there is a red flag down here, and this is where I want to kind of talk a little bit about the red flag. Hopefully you're seeing it, but the red flag is this right here, okay? The fact that we're getting a negative value for the normal force, okay, is actually the red flag. If you do the net force equations like I did here, where I already put the directions in the net force equation as opposed to using them as vectors and putting the directions in and only substituting in magnitudes, when you get a negative, it basically tells you that you've assumed something wrong in your free body diagram. So don't despair. This basically just tells us that we picked the wrong direction for this normal force. So this normal force here is in fact incorrect. Okay, this is actually in the wrong direction. Basically, what our calculation tells us is that the normal force actually has to be in a downwards direction instead. So in other words, this, whatever it's attached to here, has to actually hold it down. If it wasn't for this this support over here, this whole thing would kind of flip up and would rotate about this other point. All right. So again, if you ever get this, it just means you've made an assumption wrong about your free body diagram. In this case, I would go back and I just make that adjustment. And you should see that this would turn into a positive number. Now let's think about why that even makes any sense. So if we think about changing our point of rotation, okay, take it out from over here and put the point of rotation, let's reconsider a new point of rotation right here. All right, we'll call this point of rotation 2. And this is just for the thought experiment. But if you do this and you consider in this force of gravity, which is roughly half of this whole thing is going to have a net torque. Okay, the net torque on this is going to be in a clockwise direction, given just the force of gravity and this applied force. That means that in order to maintain rotational equilibrium, we need another torque. That other torque has to be created by this support over here, and that has to be in a downwards direction to create a counterclockwise torque to balance it out. So again, when we first started this problem, I said there was a red flag. This is where it is. After doing enough of these, you'll get a feel for it, but keep in mind that if you solve these and you use the same methodology that I've used, if you've made a wrong assumption about something, in the end it comes out as a negative, and you just know to go back and say, all right, well, it was in the other direction. All right? So our responses would be, to correctly respond to this, would be 15.3 newtons upwards, and the force normal 1 would actually, in fact, be opposite of what we drew, but it would be 1.68 newtons downwards.